For this video, I'm going to walk you through intermolecular forces, or IMFs, so the different types of them, and the properties of liquids. Intermolecular forces, or IMFs for short, are attractions between the molecules themselves. Be careful here. Intermolecular forces are not true bonds. These are just attractions in between different molecules. All right, they're not the bonds that hold atoms together. These are the attractions that bring molecules closer together. All right, so definitely need to understand that. These are not real bonds. We represent these IMFs by dashed lines. All right, so whenever an attraction forms between two molecules, we would show the attraction with a dashed line. But how many of these IMFs you have and the overall types, this contributes to certain physical properties here, like melting points, boiling points, vapor pressures, all attributed to the amount and strength of these IMFs. If you have a lot of IMFs, very strong intermolecular forces, you're going to have, say, for example, a higher boiling point because you have to break all those intermolecular forces in order to get the substance to boil. So you're going to need to think about this in terms of the IMFs themselves, but then how they relate to properties. Very important to understand that these IMFs are between molecules and they are not true bonds. Understanding the difference here between these two terms is very important. So we have intramolecular forces, all right? We have TR, all right? Just like true, TR true, okay? So intramolecular forces are true bonds. These are the forces that hold atoms together. They are much stronger than these intermolecular forces, these IMFs. Intramolecular forces are true bonds and they are holding atoms together. All right, so if you were looking at it in these pictures here, the bonds between, say, the nitrogen and the hydrogen here, or over here, the bonds between the carbon and the oxygen, those are intramolecular forces. And then the intermolecular forces, the IMFs, these are those attractive forces that keep molecules together, and they are much weaker. So you can see them in the picture represented by the dashed line. So you have two molecules here of ammonia forming an intermolecular force, which is an attraction that's keeping them together. And even up here, you can see an attraction here bringing the CO2 molecules themselves together. So you definitely need to understand the difference here. The intramolecular forces are true bonds, much stronger, and the intermolecular forces, which we're going to be focusing on here, are just these attractions, and they are much weaker. The first type of IMF we're going to look at are London dispersion forces. We usually abbreviate these LDFs. All right, so LDFs here are these instantaneous dipoles that happen due to the random movement of electrons here. Usually what happens is as these molecules collide randomly, just due to random chance, some of the electrons shift more toward one side of the atom. All right, so you can see here in this picture, you have a nonpolar atom here, a helium atom, and just randomly, due to collisions, random chance here, more of the electrons shift to the left side of this atom of helium. All right, so what happens is now you have more of the electrons on the left side, so now you have this side of this atom of helium being slightly negative. And then the opposite side, since it has less of those electrons, becomes slightly positive. Well, because this happens in this molecule, it kind of triggers kind of an effect in the neighboring helium atom here. This atom senses that there's a slight positive here, so its electrons then shift, all right, and now it gets more electrons kind of on the left side of the molecule, and they form this weak attraction. You would see the dotted line here, and they are attracting to each other. Again, this was completely instantaneous and random due to just these collisions and the random movement of electrons to one side of the atom. But this is not going to last very long. all right? Remember, this is completely instantaneous. So as these electrons shifted over, forming the slightly positive, which caused the neighboring helium atom here to have its electron shift and form this attraction, just as quick as it forms, it's going to disappear. These electrons are going to shift back to normal, which would then cause these electrons to shift back to normal, and then that instantaneous dipole, this London dispersion force that forms, will disappear. But what's happening is that this is happening all over the place. It's kind of like these London dispersion forces are forming and disappearing, forming and disappearing. But it's constantly happening here due to these random collisions. All right. These London dispersion forces will exist in all molecules. Okay. Even if it's polar or nonpolar, they're going to exist in all molecules. It's just that they are the most common type, all right, the most prevalent type here in nonpolar molecules. If you have a nonpolar molecule, LDFs are going to be the main type of IMF in those molecules. So if you can identify a molecule as being nonpolar, you pretty much know that it's going to have LDFs as its main and strongest IMF. All right. It's typically not going to have the other types of IMFs here. So another easy example of this is if we were looking at one of the diatomics, like iodine. All right. Randomly, due to collisions here, for whatever reason, more of the electrons kind of shifted to the right side of this molecule, which makes this side slightly negative. And you can even see that kind of the cloud of the electrons is more around the right side, which then makes the left side here slightly positive. A neighboring iodine molecule senses that. So its electrons on this side are getting away from that slightly negative and they shift to the right side. Well, now the left side of this one is slightly positive. You have a slightly negative and a slightly positive near each other. So they form this weak attraction that we call an LDF. Remember, this is an IMF, so it's weak and it's happening between molecules. Just as quick as this forms, it's going to go away and everything's going to shift back to normal here. So typically, this is what we see happening in non-polar molecules. So you might have to, analyze the structure and determine that a molecule is nonpolar to be able to determine that its main form of IMF is going to be these London dispersion forces. Of the three types of IMFs we are going to look at, the London dispersion forces, these LDFs, are the weakest of the IMFs. Remember, all the IMFs are weak because they're not true bonds. But the London dispersion forces are the weakest because they kind of just form and then disappear. They're not going to be necessarily forming and staying put. But the overall strength of these LDFs depend on how easily these molecules can actually form this instantaneous dipole. And we're going to look at that here on the next slide. You'll see that some are able to form this kind of instantaneous dipole a little bit more and then cause kind of stronger LDFs here. So if you look at this picture here, due to random collisions, there's an instantaneous dipole forming in this molecule. More of the electrons shift to the left side. Well, that causes dipoles then to form in the neighboring molecules. All right, so the one here on the bottom right, this one starts to be slightly negative because its electron shifted to the left, so that there's an attraction between the slightly negative and the slightly positive. And then the one here on the left, its electrons are kind of shifting to the left side of the molecule to get away from the slightly negative here that formed in that middle molecule. And then they would form an LDF between the slightly negative and slightly positive. And again, just as quick as they form, everything's going to go back to normal and they're going to disappear. But these are going to be the weakest of the IMFs, but their overall strength needs to be analyzed further here because it depends on how easily a molecule can form this instantaneous dipole. We call that ease of distortion of the electron cloud, that ability to form these instantaneous dipoles, we call that polarizability. This is a big AP term. You got to get used to using the vocabulary here, but polarizability is just talking about how easily that electron cloud in a molecule can be distorted to form these instantaneous dipoles. And the basic gist here is if a molecule has more electrons, and basically if you have a greater molar mass, you're going to have more electrons here. Realize the molar mass helps you. If you can identify that a substance has a greater molar mass, that's going to be important, but really it's the electrons. If a substance has more electrons, it's going to have greater polarizability, basically a greater ability to have this electron cloud become distorted to form these instantaneous dipoles. So then it's going to have stronger LDFs. Basically, if the molecule can form these instantaneous dipoles easier, well, then it's going to form those LDFs and they're going to be stronger. So more electrons mean greater polarizability, which means stronger LDFs for a particular substance. All right, you typically only talk about this polarizability when you're trying to explain LDFs between substances. A lot of times when we might be looking at the other types of IMFs, people try to use polarizability to explain, and that's not really where it's useful. It's typically used here when we're talking about LDFs. So if we want to look at an example here, fluorine and chlorine are halogens, all right? They are gases. But as you go further down the periodic table, bromine and iodine, Br2 and I2, are not. Bromine's typically a liquid, iodine is typically a solid that can sublimate. And if you look at the masses here, it makes sense. As you go down the periodic table, you would expect the mass to increase. So basically, as you go from fluorine to chlorine to bromine to iodine, you have more and more electrons. So as you get more electrons, the bromine and the iodine have greater polarizability, which means their LDFs are stronger. Those IMFs, all right, in particular here, these LDFs are much stronger, so it keeps those molecules closer together, which makes them stay as a liquid or as a solid. Whereas the fluorine and the chlorine, they have these LDFs, but they don't have as much polarizability. Basically, their electron cloud cannot be distorted as easily, so they're not held together as close, so they are gases. All right, so you definitely need to understand this idea of polarizability, and you need to use this vocab when you're explaining this for LDFs. And again, just to point out, it's the electrons here that are important for the AP exam. The mass keys you in. You know that if a substance has more mass, it's going to have more electrons. But when you're explaining this, if a substance has more electrons due to a greater mass, that means it's going to have this greater polarizability and then stronger LDFs. And then you got to think about, what do stronger LDFs then mean for the properties of a substance? But definitely understand this idea of polarizability and having the electron cloud being easily distorted here with more electrons being present. This slide is just showing this idea of going down the halogens and having more electrons, having a greater polarizability, so therefore having stronger LDFs, which contribute to the properties here. We already went over the phase properties. Chlorine and fluorine are gases because as you go down, you get more electrons, which means greater polarizability, stronger LDFs. These guys are closer together, so they stay as a liquid or a solid. But you can even tie this in with melting point and boiling point. Look what happens as you go down the halogens. The melting points and boiling points get much greater as well, because as you increase the electrons, you're increasing the polarizability, which means stronger LDFs. So if you want to melt or boil these substances, if they have stronger LDFs, you have to break those LDFs in order to melt or boil them, which takes more energy if they're stronger. Okay, so this all directly relates to having more electrons, more polarizability, which means stronger LDFs, which you have to input more energy to break. All right, so you need to understand this idea of more electrons, meaning more polarizability. The second type of IMF is dipole-dipole, all right? These are attractions between molecules that have permanent dipoles, all right? So typically, this is going to be the stronger IMF in polar molecules. So if you can identify that a molecule is polar, you know that it's going to have dipole-dipole forces as its strongest form of IMFs. It will still have LDFs, it's just that dipole-dipole are stronger. And the reason these are stronger is because unlike LDFs, these are not going to disappear. For LDFs, the dipoles are instantaneous. They form and they disappear. For molecules that have dipoles, for polar molecules, they always have that region of slight negative and slightly positive, and it doesn't go away. So when these dipole-dipoles form, they're not going to disappear. That's what makes the dipole-dipole IMFs stronger here. And basically what happens is, the easiest way to see this is in this example here of HCl. It's a polar molecule, so the chlorine always is slightly negative because it's hogging those electrons, and the hydrogen is always slightly positive, and it's never going to disappear. So what happens is they kind of align themselves here. This slightly negative chlorine will align itself next to another molecule of HCl, the slightly positive hydrogen on another molecule here, and they form this weak attraction, which we call a dipole-dipole IMF. And the thing is, this is not going to disappear like the LDF did because the chlorine is always going to be slightly negative and the hydrogen is always going to be slightly positive because the molecule is polar. Make sure you understand here that even though these dipole-dipoles are stronger than the LDFs, they are still weak because they are IMFs and not true bonds. They're only about 1% as strong as an ionic bond. So they're still pretty weak. It's just that they are stronger than LDFs here. All right. And the larger the dipole difference, all right, so the larger the difference here in the dipole, if this atom is very electronegative, then the attraction here gets even stronger. All right, so this dipole-dipole would be even stronger if you had more and more electronegative elements involved here. So very important again, if you analyze a particular molecule and realize it's polar, you can pretty much assume here that it's going to have dipole-dipole IMFs as its strongest IMF, but it would still have LDFs as well. It's just that they're not going to be the strongest type here in these types of polar molecules. This picture is just showing you these dipole-dipoles that would be forming between the molecules themselves. Remember, the true bonds would be happening between the atoms. These dashed lines are the dipole-dipole IMFs that are weaker, but they are these attractions that are keeping the molecules here closer together. So if this was a beaker of HCl, you'd be seeing these dipole-dipole attractions happening all over the place between all the different molecules. And unlike LDFs, they're not just going to form and disappear. That's what makes them stronger. And keep in mind here that these forces will start to dissipate or disappear with increased distances. So if you have like a gas, you're not going to expect these dipole-dipoles to be kind of as much or as strong because the gas molecules themselves are kind of further apart moving around. So that's just something to pay attention to. The third type of IMF is called hydrogen bonding. The name is a little confusing because it's not a real bond, okay? So that's very important. It is an IMF, all right? It is basically a just stronger version of a dipole-dipole. If you understand what dipole-dipole is, hydrogen bonding is just a stronger form of that, right? In order to have hydrogen bonding, it's not just if you see a hydrogen in a molecule, it has hydrogen bonding. No, that is something you need to make sure you understand here. You're only going to see hydrogen bonding when you have hydrogen bonded to nitrogen, oxygen, or fluorine. If you have hydrogen in a molecule, but it's not bonded to nitrogen, oxygen, or fluorine, then you don't have hydrogen bonding. All right, and be careful. Just because a formula has nitrogen in it, say, or oxygen or fluorine, and a hydrogen, you need to make sure that the hydrogen is actually attached to one of those elements in order for this hydrogen bonding to occur. Basically, if you remember back when we were doing dipole-dipole, we said that as you increase kind of the electronegativity here of these elements, you create these stronger dipole-dipoles, and that's basically what hydrogen bonding is. These three elements are very electronegative, so they kind of hog the electrons so much that you create a stronger version of a dipole-dipole here. All right, so it's when hydrogen is bonded to one of these three very electronegative elements. And it's just like dipole-dipole, you have a slightly negative of one molecule coming nearby, a slightly positive of a neighboring molecule, and they form this weak attraction. All right, it's not a true bond, it's still an attraction, it's just the strongest of the three IMFs that we are going to look at, but still way weaker than a true bond. And this hydrogen bonding is very important for the properties of water and for DNA as well. So you should understand how this hydrogen bonding would work. AP has asked in the past, draw some water molecules, show the hydrogen bonding. So you would have to understand this. If you look at the picture here, this molecule of water, you have the slightly negative oxygen. All right, remember the oxygen is hogging the electrons, and it kind of comes close nearby. You have this slightly positive hydrogen. Remember, this is always going to be happening. Water is a polar molecule. So when you get those opposites nearby, they form this hydrogen bond. And it's a hydrogen bond, not just a dipole-dipole, because you have hydrogen bonded to oxygen here. And remember, you would need to show this as a dashed line. And you can see that kind of happening all over down here with a bunch of different water molecules. So it's the strongest of the three IMFs. It's just basically a stronger version of a dipole-dipole. It is not a true bond, though, but you must have hydrogen bonded to one of these three elements, nitrogen, oxygen, or fluorine. So again, this picture is just showing you how these hydrogen bonds can form between the different water molecules. You need the slightly negative oxygen nearby to a neighboring slightly positive hydrogen, and they form that weak attraction, the hydrogen bond that we show as a dashed line. Remember, these are between the molecules, not the actual bonds here. If we look at some of these properties on the periodic table, we can see how big of an impact hydrogen bonding can have here. If you look at this graph, basically, we would expect boiling point. All right, this graph is showing boiling point, comparing it to the row on the periodic table. We would expect that as you increase the molar mass here, that the boiling point would increase as well, because you have more electrons, therefore greater polarizability, therefore stronger IMFs, which have to be broken. So therefore you need to put more energy into it in order to get it to break those IMFs and in order to boil. So basically, if you look here, typically that's what we see happening on the periodic table. As we increase the period number and we get more molar mass, greater polarizability, we see the boiling point increasing. All right, but notice these lighter hydrides, the ones with oxygen, fluorine, and nitrogen, they actually break the trend. Carbon doesn't. All right, when you have hydrogen here with carbon, it follows the trend. All right, but these guys, the nitrogen, oxygen, or fluorine bonded with hydrogen, they are much higher. And that's because of the hydrogen bonding. In order to get these substances to boil, you have to break all those IMFs, and they have much stronger IMFs because they have the hydrogen bonding present. All right, so if you kind of place where they should be, they all kind of should be down in this region, and then they should increase as you increase the period number, increase the molar mass. But that's not what we see because of the hydrogen bonding. That hydrogen bonding is much stronger than the other IMFs, and these are the only ones that have it, so they have a much higher boiling point here. So definitely make sure you understand this idea and you understand this graph. So now we're going to try to apply this to some molecules. We want to identify the main or the strongest type of IMF in each of these substances. This is what you might need to do. You might be given a question and you have to identify the main or the strongest type of IMF in each. It's important to understand here, though, this bottom part is really important, all right? If you have hydrogen bonding present in a molecule, you have all three types of IMFs present: LDFs, dipole-dipole, and hydrogen bonding. If you're asked a question on the AP exam, what are, the IMFs present in a molecule that has hydrogen bonding, you have to list all three. If they ask just for the strongest type, then you would say hydrogen bonding. All right. If you have a molecule that just has dipole-dipole, it has dipole-dipole and LDFs. The dipole-dipole is its strongest or its main form, but LDFs are still there. And if you have a molecule that has just LDFs, well, then it doesn't have anything else as its IMFs except the LDFs. So that's a big thing to understand here. So for the first molecule, CCl4, if we just want to identify the main type, in order to do this, you have to figure out how these atoms are bonded together. If you can do this just by looking at it, then you could probably figure it out. If you need to draw it, do a dot structure, then definitely do that. So for the first one here, CCl4, if you didn't realize, it would have a structural formula that would look like this. All right, that structure is going to be non-polar. All right, so if it's non-polar, its main or strongest type of IMF is going to be those LDFs. All right, that's how you figure out the main or the strongest type of IMFs here. You have to figure out if it's polar or non-polar and go from there. For the second one, I'm not going to draw the dot structure because I see this OH here, all right? That hydrogen would be bonded to O, and anytime you have hydrogen bonded to N, O, or F, you know you're going to have hydrogen bonding as the strongest type. But it will also have dipole-dipole and LDFs present. It's just that the hydrogen bonding is its strongest type of IMF here. Remember, just having oxygen and hydrogen in a molecule, if they're not actually bonded together, then you don't have hydrogen bonding. But if you drew the dot structure for this, you would see the hydrogen is bonded to the oxygen. For the third one here, we have C4H10. That's going to be butane. Just seeing hydrogen doesn't mean it has hydrogen bonding. There's no nitrogen, oxygen, or fluorine in it that the hydrogen is bonded to. So that's out. If you draw this molecule, it's just going to be a chain of carbons with hydrogens attached to all of them. It's going to be completely non-polar. So this one would be LDFs as well. And then the last one here, HF. HF would be a polar molecule. So dipole-dipole would be its strongest IMF, but realize it would also have LDFs present as well. So typically here, if you're trying to figure out the main type of IMF or the types of IMFs in a molecule, draw it, determine if it's polar or non-polar, and then go from there. Now we are going to start going through some of the properties here of liquids, and then you do have to think about how the IMFs affect these properties. So some of these are pretty quick, some of them are pretty self-explanatory, but surface tension in a liquid is a resistance of a liquid to increase its surface area. Basically, when you see a liquid kind of beating together here, or kind of like how water can overflow a container without fully spilling out, that's surface tension. And basically, why this is happening is because you have this attraction forming between the molecules here on the surface. So typically what you'll see is if you have a molecule that has more IMFs, you're going to have more surface tension because those IMFs are greater, which allows the surface tension to be higher here. And water has hydrogen bonding, so it makes sense why this is so great in water. More IMFs, greater surface tension. Capillary action is when you have this spontaneous rising of liquid in a narrow tube. All right, so if you have a very narrow tube and you put it into a liquid, it can rise up the tube on its own spontaneously, and that's due to IMFs. Typically here, greater IMFs, greater capillary action. It's going to rise up the tube much higher. So we need to understand what's going on here, some of these terms. Cohesive forces are forces between the molecules themselves, and then adhesive forces are between the molecule and the container. So for water, water has adhesive forces that are greater than the cohesive forces. Basically, the attraction for the water molecules to the container is much greater than the attraction between the water molecules themselves. And this is why you get that concave meniscus forming with water. If you remember, you always would read in the graduate cylinder at the bottom of the meniscus, but the reason that's happening is because the adhesive forces in the water are greater than the cohesive forces between the water molecules themselves. So the water is kind of attracting to the sides of the container here more, and it's kind of rising up a little bit. And then the cohesive forces would be between the molecules of water themselves. But then something like mercury actually has a convex meniscus. All right. The adhesive forces are not as great as the cohesive forces between the mercury itself. All right. So again, you got to think about IMFs here, but as long as you have greater IMFs, you would expect to see greater capillary action, higher rising in the tube. So you can see this idea of capillary action here in this picture, and typically the narrower the tube, the more surface area there is, the higher up it's going to go. So this is the same substance here in all these tubes, but notice as the tube gets narrower, the liquid travels further up the tube. And this is basically how we get water, going through the stems here, traveling up plants and large trees. This capillary action and these attractions help bring the water from kind of the roots all the way up. And you can actually do this if you could get the stem to split properly. You put one of the part of the stems in colored water, the other part in regular water, and you would actually start to see some different coloration here in the flower itself. Viscosity is another property here of liquids. It basically means a resistance to flow. All right. So if a liquid doesn't want to pour, we would say that it has a high viscosity. It has a high resistance to flowing. Basically, this would increase with greater size and lower temperatures. You could think about some liquids maybe that were at a lower temperature that they don't want to pour as much. We would say that they have a higher viscosity at these lower temperatures. Typically here, more IMFs, you're going to have a greater viscosity. Basically, if the IMFs are stronger, it's holding those molecules together more, so they're not going to want to flow as much. So a substance that has a low viscosity would be easier to pour out, more would kind of flow out, and a substance that has a higher viscosity, less would come out as you're pouring it. Think of something like honey. As you're trying to get it to come out, it's kind of resisting the flow, so it would be a high viscosity. All right, more IMFs, stronger IMFs, you're going to have a greater viscosity. Volatility is the ability to evaporate, or basically the ability to enter into the gas phase. So when we're talking about something being volatile, we're talking about a substance that can easily go from the liquid phase and enter the gas phase. This one is opposite of the other ones, right? If you have more IMFs, stronger IMFs, you're going to be less volatile. And you really need to think about that. If your IMFs are stronger, the molecules are going to be held together more, so less of them are going to enter the gas phase. So it would be less volatile. If you look here in these pictures, we have two organic substances. We have toluene on the left and benzene on the right. And if you look at the picture, this is the liquid phase, and you should be able to identify that because the molecules here are much closer together. And then here you see the gas phase. Well, if you notice, the one on the left, all right, would be less volatile because there's less of these molecules in the gas phase. And then the benzene here on the right is going to be more volatile because you have more of those molecules entering the gas phase. So we know if this one is less volatile, it has higher IMFs or stronger IMFs. So if you look at the structures here, can you figure out why this one on the left has more IMFs? The first thing you would need to do is, analyze these structures. Do you see hydrogen bonding? Well, no, because you don't see nitrogen, oxygen, or fluorine attached to hydrogen. Uh, they're not going to have dipole-dipole because both of these molecules are nonpolar. So they're both going to have LDFs. But why are the LDFs of the toluene greater? Well, if you notice, it has this extra CH3 group here. Basically, if you did the molar masses of the two and compared, the toluene is going to have a greater molar mass because it has that extra carbon. So if it has more molar mass, it has more electrons, which means it's more polarizable, which means its IMFs, its LDFs here are going to be stronger. So if the LDFs are stronger, those molecules are going to be held together tighter and less are going to enter the gas phase here. So it's going to be less volatile. Just remember, you need to know what the definition of volatility is. All right, basically the ability to enter the gas phase. And if you have more IMFs, you're going to be less volatile. It's kind of opposite of the other properties. Now we need to look at what happens here with IMFs when we're trying to form a solution. Basically, if you're trying to get something to dissolve in a solvent, what's actually happening and why is this taking place? So, a couple things here first. If you're trying to get a substance like, say, salt to dissolve in water, what's happening? Well, first, and this always takes energy, all right? You have to separate what we call the solute-solute IMFs. So any of the IMFs that are in the substance, in the solute that you're adding here, they have to be essentially overcome or broken. So that's going to take energy. But you also have IMFs in the solvent itself. So typically here, the water. You have to use energy to break or overcome those IMFs. So these two things must happen first, and they both require energy. You have to overcome the IMFs in the solute, and then you have to overcome the IMFs in the solvent. All right. But then also, now the solute and the solvent are going to interact here. So there's going to be new attractive forces forming between the solute and the solvent itself once you mix them, and this is going to give off energy. All right, so both of these things are happening. You must overcome the IMFs in the solute. We call that the solute-solute IMFs. You must overcome the IMFs in the solvent. We call that the solvent-solvent IMFs, and that takes energy. But when the solute and the solvent interact and form new IMFs, all right, energy is given off. So as you'll see here, as we keep going with this idea, you're no longer allowed to say like dissolves like on the AP exam. All right, we know that polar substances will dissolve in polar water. All right, and you can't say, well, that's because of like dissolves like. It might help you remember the idea, but now you'll need to explain it here in terms of the IMFs, as you'll see here on the next slide. So this requires a little bit of thinking. We already know that like dissolves like. We're just no longer allowed to say that anymore. So polar or ionic substances, because ionic substances have, that plus minus region of charge, they dissolve in polar substances. So why? Well, let's look at this. We already know you have to overcome the IMFs in the solute and overcome the IMFs in the the solvent. So we say that the delta H here, that just basically means the change in energy. The amount of energy to overcome the IMFs in both the solute and the solvent, in this case the water, is quite large. All right, because these substances are perhaps going to be polar or ionic, it's going to take a lot of energy to separate the solute-solute IMFs and the solvent-solvent IMFs in each. All right, it's going to take a lot of energy to do that. However, when the newly separated solute and solvent interact with each other and form new IMFs, the amount of energy that's given off is very large, okay, as well. And it's actually much larger than the amount of energy it took to separate the IMFs in the solute and the solvent. So you really got to think about it. It takes energy to separate the IMFs in the solute and the solvent. It takes a lot of energy, but when the solute and the solvent form new IMFs with each other as they dissolve, more energy is given off, is released when these new interactions form. So basically, the reason why the solute dissolves because enough energy is given back essentially and more than what you actually put in to overcome the IMFs in the solute and the solvent. So it took energy to overcome the IMFs in the solute and the solvent. It's just that when the solute and the solvent interact with each other and form new IMFs, you get more energy back than what you put in. And the same thing would happen here for nonpolar substances. Nonpolar substances would dissolve in nonpolar substances for the same exact reason. It would take energy to separate the solute and the solvent IMFs, but when they interact with each other, the solute and the solvent are going to attract and give off more energy than it took to kind of separate the IMFs initially. So you got to understand this idea and be able to explain it in terms of what's happening here in terms of the IMFs and the energy. So we know that like dissolves like, which we're not allowed to say, but so then substances that are not similar don't dissolve. So polar or ionic substances don't dissolve in non-polar solvents. Well, why? What's happening here? All right, you need to understand that it's going to take energy to separate the IMFs in the solute. It's going to take energy to separate the IMFs in the solvent. And then when the solute and the solvent are interacting with each other and forming new IMFs, you don't get as much energy back, okay? So the energy released when the new solute and solvent IMFs are going to form, you don't get as much energy back as you put in, all right? So essentially here, the energy required to overcome the solute-solute IMFs and the solvent-solvent IMFs is much greater, all right? You don't get as much energy back when the solute interacts with the solvent, all right? So essentially, you are in the hole, if you will, all right? You paid $5, but you're only getting $2 back worth of energy, so it's not worth it. So these polar substances will not dissolve in a non-polar substance and vice versa here. You put more energy into separating the IMFs than you actually get back when the new IMFs form. So you got to be able to explain this in terms of the energy and the IMFs for why a polar substance won't dissolve in a non-polar substance and vice versa. I think this summary slide is important because it can help you really kind of narrow down these ideas. But if you're trying to figure out why a polar substance would dissolve in a polar solvent here, basically, if the energy released when the solute and the solvent interact is greater than the energy needed to break the IMFs in each, the substance will dissolve. Basically, you get more energy back when the new kind of substances interact, when you dissolve, than it took to separate initially. But if the energy released when the solute and the solvent interact is lower than the energy needed to break the IMFs in each, the substance will not dissolve. Basically, you're not getting as much energy back as it takes to put into the separation, so it will not dissolve. So oil will not dissolve in water because you don't get as much energy back when the oil and the water molecules interact with each other. But in this case, sugar would dissolve in water because even though it takes energy to overcome the IMFs in each, you get more energy back when the new IMFs form when the dissolved solute interacts with the solvent. All right, so you definitely need to understand this idea, and you can no longer say like dissolves like. A couple more things here to understand about IMFs. Gases are typically going to have weaker IMFs because they have a lot of motion, and typically the molecules are further apart, so their IMFs are not as strong. And then solids and liquids are going to have stronger IMFs, and they're not going to have that motion. You would expect the solids to be maybe a little bit closer together here, but you can see here if you're looking at the states of water, when it forms ice, you can see those attractions there between the water molecules would be pretty strong. Same thing for water, but then steam is moving around, it's further apart. You're not going to see those IMFs really present. All right, so this is just kind of making sure you understand the difference here, even between solids, liquids, and gas in terms of the IMFs. If you're trying to compare substances and you're trying to think about the strengths of the properties here, just remember that the LDFs are always the weakest, and then the dipole-dipole, and then the hydrogen bonding. So if you can identify that a particular molecule has hydrogen bonding, you could pretty much expect it to have the strongest IMFs, and therefore perhaps maybe the strongest properties here. A couple other things. If you have molecules that are completely linear or in a line or kind of maybe very flat, you would expect to see more IMFs. Right? And this is typically for these larger organic molecules, long chains of carbons and hydrogens. Don't try to really look at this in terms of normal molecules. And then the opposite is true here. If you have these organic molecules that are kind of spherical or maybe have more branching, you would expect the IMFs to be lesser because they can't maybe get as close together and form those stronger IMFs. But again, this is more for these organic molecules. These larger organic molecules have lots of carbons and hydrogens in them. We really wouldn't be looking at this with normal molecules. And something just to take note, sometimes if a molecule has a really large electron cloud, really large, maybe molar mass, sometimes the dispersion forces are actually the strongest here. All right, so there is kind of a little bit of variation, but definitely realize here that dispersion are the weakest. So the London dispersion are the weakest, then dipole-dipole, then the hydrogen bonding. So I want you to arrange these molecules in order of increasing boiling point. So low to high. You're going to have to look at the structures here, think about the IMFs, and then figure out the correct order. So I would pause the video, try to come up with this, try to explain it, and then when you rejoin the video, you'll see the order and then I'll provide the explanation. So I would pause the video right now and try this. All right, so the order is kind of written here. So if we look at this, the propane would have the lowest boiling point because it's going to have the weakest of the IMFs. It is completely nonpolar, so it would have LDFs as its only IMF, which we know is the weakest of all the IMFs. All right, and then the ether would be in the middle because it has this O here, but the O is attached to the carbons. That's not going to be hydrogen bonding. It's actually going to have a dipole-dipole. Whenever you see an O in a molecule like this, whether it's kind of in the middle or a double bond to an O, that typically leads to polarity here. And that means that this molecule would have dipole-dipole as its strongest IMF. It also has LDFs present. It's just that the dipole-dipole would be there, which is stronger than the LDFs. So this would take a little bit more energy to break those dipole-dipole IMFs in order to get this one to boil. And then the strongest would be the ethanol, because if you notice, this has the O bonded to the H. That would have hydrogen bonding as its strongest. It still has dipole-dipole. It still has LDFs as well, but it has the hydrogen bonding present, which would be the strongest IMFs. So if you want this to boil, you have to break those hydrogen bonds, which are stronger. So it would take more energy to get this to actually boil here. All right, so you do need to pay attention to polar, non-polar, and then consider the IMFs to determine properties here. And this is something you need to be able to do.